Now we will discuss the flow inside a tube, called a pipe flow or internal flow. Let's consider a circular pipe. As a fluid enters the pipe, let's assume it has a uniform velocity across the section of the pipe. Now we understood viscosity and we have studied the no slip condition at the wall. We mentioned in the last lecture that any fluid adjacent to a solid wall does not slip at the wall. It has the same speed as the wall speed. So if the wall is stationary, the fluid exactly adjacent to the wall would be stationary, would have zero velocity. This fluid which entered this pipe at a uniform velocity would see an immediate stop to a layer of fluid in immediate vicinity of the pipe wall, and so after a little time the velocity profile would look like this. The effect of viscosity has penetrated up to this depth from both walls. At a little further distance, this penetration would be further down, more, till all the fluid in the pipe is affected by the viscosity. This penetration of the viscous effect is the same thing that we discussed in the last lecture, the diffusion of vorticity. This ultimately, in this pipe, we will develop a parabolic velocity profile that you studied in high school. Notice one thing, the velocity at the center, which is maximum, is increasing as you go from left to right. Why? Because same amount of fluid must be flowing across each section. And since in the later sections more of the fluid is slowed down, so the fluid at the center must have speeded up. In fact, you would study later on that the maximum velocity at the center is twice the velocity of the flow at the entrance of the pipe. In this picture, the shaded area is the area that has been affected by viscosity. The remaining area is unaffected area. It's called the core area. After this length, the velocity profile does not change. And we say that the flow is fully developed. It is between this and this that the velocity profile changes. We call this a developing length, an entrance length of the pipe, where the flow is developing. Developing flow, and then fully developed flow after the velocity profile has once become parabolic and the viscous flow covers the whole region. How long is this developing flow region? The calculations have shown that this is proportional to the diameter of the pipe and to the Reynolds number. For laminar flow, this length could be quite a bit. This length could be up to 100 diameters in laminar flow. But in turbulent flows, this length is quite low. We will discuss this too later. Here we are comparing the flow profiles in the laminar flow and the turbulent flows. In laminar flows, the maximum velocity is much larger than the average velocity. Not so in turbulent flow. In turbulent flow, the central region is quite flat. The gradient of velocity at the wall is much larger in the case of turbulent flow than in the case of laminar flow. Since the shear stresses are related to velocity gradient, so shear stress on the wall in turbulent flow is much more than the shear stress in laminar flow for the same mean velocity. Much larger shear stress on the wall has much larger pressure drops, much shorter developing lengths in turbulent flows, as we discussed earlier. Most pipe flows are turbulent. In fact, we would later on learn that the pumping cost when the flow is turbulent is most economical. We'll discuss that issue later on. Water flowing in a 10 centimeter diameter tube, which is about 4 inches diameter, at 20 centimeters per second is likely to be turbulent. Most flows in the pipes are turbulent. There's another property of internal flows that we want to discuss. Consider the first picture. Here we have flow in a converging diverging pipe. The length of the converging portion is much smaller than length of the diverging portion. Let's assume the fluid is water, an incompressible fluid. As the flow enters from the left, the velocity of the flow must increase, because if we are passing the same flow, as the cross-sectional area decreases up to the throat, the velocity must increase. The yellow line shows the variation of velocity. Then in the diverging portion, the velocity decreases again. What happens to pressure? As the velocity increases, the pressure decreases. In accordance with the Bernoulli theorem that is you studied in high school, and which we will cover here in much more details in a later chapter. The pressure increases as the velocity decreases, and then the pressure increases again after the throat as the velocity decreases. But if the length of the diverging section is reduced, like in the lower picture, you see very interesting thing. The flow here separates at the throat and comes out as a jet. And if it comes out as a jet, the velocity does not decrease. So while in the converging portion the velocity is increasing, the yellow line, in the diverging portion the velocity does not decrease. And because of this, the pressure does not recover. Pressure does not increase. And so there is a decrease in pressure down this short nozzle. And this results in loss of energy. We have to be very careful about the diverging portions because the flow tends to separate. I end this lecture with a description of two pipe fittings. One is in which there is sudden increase in the cross section of the pipe, sudden expansion of the pipe. The flow tends to expand, but the flow separates at this region, developing an annular dead water region. The fluid in this region does not move forward, it's just recirculating there. The velocity decreases like this, but because of losses, the pressure does not change very much. Since the velocity is decreased, if there was no flow separation, the pressure would have increased, but the pressure does not increase. This means there is a pressure drop at a sudden expansion. And if we are pumping water, that would mean we have to apply more pressure difference, we have to expend more power in pushing the water through this sudden expansion. Similarly, in a sudden contraction, because the flow is slowing down here, there is a separation. Here, there is an annular vortex here. Then at the sharp corner, there is separation again. The fluid cannot turn sharply, and so we have an annular vortex sitting right there. All this results in head losses. This is the minimum cross section of the flow. It's called vena contracta in fluid mechanics. Pressure decreases because the velocity increases. Thank you very much.